All right, so I will quickly go into what the Filecoin Crypto team is because, we've talked about the Lotus team and we've seen the forks, but there's also the Filecoin Crypto team, which works kind of on the lowest level of the proofs. And so currently we are 5 people, and we have also I'm here, I'm Volker, but there's also Shawn, which will later present the roadmap. And then we have also Jake, Nemo, and Artem. So Artem will do the actual deep dive. He sadly can't be here because not everyone is as free to travel as we are. So it will be a pre-recorded talk, but he will watch it on YouTube. So afterwards there will be a Q&A and he will also be able to answer the questions. And so what the team is actually doing is we are implementing the cryptographic core functionality. And related to this, there's many things. So of course, maintaining things, but also keeping things secure. So if there's any vulnerabilities in cryptographic protocols, we fix them. Or this is specifically what I'm working on GPU acceleration, because else it would take way much longer to do the proofs. And things that we've also talked about or heard about, things like new proofs, like snap deals that just shipped this year. We were responsible for the implementation. And currently with the current proving system that we will hear about, there's a thing called trusted setups where the short version is you have a long running process that many parties are involved and it runs over weeks and weeks, and then you need hours and hours of verification, and we make this a smooth process, and it takes a lot of time. All right, but now I will get into the talk.
Hello everyone, I'm really excited to give a talk on this event representing my FilCrypto team. Despite it's covering quite technical aspects of Filecoin's proof stack, I try to make it easy to understand for a wide range of folks in PL ecosystem, including people who are not engineers. Nonetheless, I think it can be useful for both engineers, potential future newcomers to our team, and to those who joined Protocol Labs recently, and also engineers who may develop external products on top of the protocol. The main idea for this report is composing knowledge base and making overview of proofs stack utilization in Filecoin protocol from a crypto engineering point of view. I'll tell you about replication proofs, proofs of spacetimes, how they are used in Filecoin, and try to answer the question why are they used in this way. Okay, so I will briefly recap about Filecoin basics in order to create a context, and then I will switch straight to the proof stack. So Filecoin, being a globally distributed storage provider, is a network of individual storage providers of miners and public validators or clients. Similar to regular centralized storage providers, Filecoin supports basic data operations like creating the data, updating, retrieving it. Every individual entity in the network does not trust to other entities. That's why Filecoin has to provide specific cryptographic enforcements that mentioned operations with the data were performed correctly. This is being implemented with the help of cryptographic primitives called proving systems. Proving system operates with abstract prover and verifier, where prover attempts to convince verifier in correctness of some well-defined statement. Prover is always an individual storage provider that attempts to convince rest of the network, clients and other storage provider who are verifiers in this case, that data operations are being performed correctly. Considering this, at this stage, Filecoin uses 3 mechanisms: Proof of Replication, PoRep, which is used to enforce valid creation or registering the data in the network. Upgrade mechanism is used for the data modification. And finally, so-called WindowPoSt proof, which is used to enforce that during particular time data is available for retrieving. Filecoin can be considered also as a blockchain, so we can also distinguish block miners among Filecoin storage providers and chain validators among Filecoin clients. In order to support correct blockchain operations, there are two additional proving mechanisms, WinningPoSt Proofs and election proofs. They are quite supportive in a sense that they do not explicitly involved into data operations like creating or updating the data. However, they are quite important for security against fundamental blockchain threats like grinding, as Filecoin uses proof of storage stake consensus, and cyber attacks. Okay, if we take a look at our Filecoin white paper, we will see that the idea of proving the fact of storing some data is not actually new. There are some well-known approaches that allow user to check whether its storage provider is still storing outsourced data in a very efficient way, much more efficiently than downloading the data. PDP, which stands as Provable Data Possession, and POR, Proof of Retrievability schemes that implement mentioned approaches, considered centralized storage providers, while Filecoin requires some additional guarantees due to its decentralized nature. That is why Proof-of-Replication plus Proof-of-Spacetime bundle inherits challenge-response nature of PDP POR schemes, but also provides additional security against following fundamental attacks. It's a Sybil attack, where malicious storage provider may create multiply fake identities and tries to get more reward for the physically non-existent copies of the originally stored data. Outsourcing attacks, where malicious miner tries to collect reward for the stored data which is actually delegated to other storage providers and relying on fast fetching the data. And the generation attack, where malicious miner claims to store a large amount of data without possessing enough storage, and instead of actually storing the data, it generates it by demand using smaller program. So in the rest of the talk, I will try to explain how combination of proof of replication and proof of spacetime help in provision security against mentioned attacks and allows satisfying mentioned requirements. Okay, now we are starting from PoRep, proof of replication. It is always performed by storage provider when new data is registered in the network. In Filecoin, data is stored in a form of 32 or 64 gigabyte sectors, and initially, a life cycle of the data in the network starts from zeroed sectors. We call them committed capacity sectors. They appear when storage provider allocates or commits its empty storage to the network, and eventually sectors are being upgraded and the user's data from deals is being written to the committed empty sectors. Sealing the sector starts from representing its data as a Merkle tree. Here on a slide for simplicity I used one base binary tree with 15 leaves, but in practice for 32 gigabyte sectors it is millions of leaves, where each leaf is 32 bytes. Also for optimization purposes we use more complicated trees like octrees, where parent node is constructed via hashing 8 child nodes instead of 2 as in binary trees, and even compound trees constructed from subtrees. Once we've done with Merkle tree construction over sectors data, we can convince verifier that we indeed have sectors data in the storage by sending inclusion proofs of particular leaves. The pointers to random leaves are called challenges, and those challenges are selected by verifier. So later, after registration the sector in the network and after obtaining Merkle proofs for challenged leaves from the storage provider, verifier can very efficiently, much more efficiently than comparing data bit by bit, check whether particular data parts are indeed stored by storage provider. Every sector is completely unique piece of the data within overall Filecoin's distributed storage. It has complex identifier called replica ID, computed from set of separate identifiers. comd is a root of the Merkle tree that is built on top of raw sectors data. Obviously, it is impossible to modify the sector's data without modifying its commitment, and since it is included into replica ID computation, which is used as an input parameter for proof computation, we will see it a bit later. Publishing this commitment in the blockchain guarantees immutability of the sector's data until a legitimate upgrade will be performed. Sector ID is a unique identifier of this sector. Prover ID is an identifier of particular storage provider which stores this sector. Ticket parameter provides a link to particular block in the chain, and finally seed is used as a randomness for the challenges deriving. Some more specific info about ticket generation and verification is provided via link below. So ultimately, as you might notice already, one of the main tasks of PoRep proof is guaranteeing that particular storage provider has saved the particular sector in its storage and committed to store it from now within some period of time, which is one of high-level design requirements. Another design requirement to the proof of replication is provision a security against generation attack, where malicious miner tries to work in mode of performing infinite sealing the sector one by one, generated via a small program like pseudo-random generator, and registering them in the network, trying to exploit consensus and increase the likelihood of winning a block reward. To prevent this, PoRep is designed to be computationally slow sequential process that cannot be easily parallelized. As far as I know, the ideas for the PoRep construction that fits mentioned requirement were taken from following papers that describe how to use directed acyclic graphs in order to achieve memory hard function suitable for proving space and replication, which is actually our case in Filecoin. The core property of such graph is that it can deterministically generate arbitrary number of derivative nodes from some initial node, which is A in this example, and it will never form a closed loop, unlike cycled graphs, so that any child node will never point to the parent one. PoRep uses such graph in its internal encoding process, which has configurable complexity. The idea behind encoding process is following. Original sector's data is divided to nodes, which is N0, N15, marked red, and with the help of directed acyclic graph, each node is mapped to so-called encoding labels, label 0, label 15, marked blue. For each given node, treated as a child node, a set of parent nodes can be deterministically derived using a cryptographically strong Feistel-based permutation that lies in a basis of particular directed acyclic graph in Filecoin protocol. So this produces us first encoding layer. Then repeating the process and feeding layer produced on previous stage, the second encoding layer can be derived, then third, then fourth, and so on until necessary complexity will be achieved. Obviously, we cannot obtain next encoding layer without computing previous one, which gives us sequential computation with configurable complexity that cannot be parallelized easily. If we want to increase replication complexity, when, for example, new, more powerful CPU becomes available in market, it is sufficient to add one or more layers computation to the encoding process. Here there is a table that represents how labels for the first layer are computed. What is interesting is that the relation with the original sector's data is achieved via mixing replica ID, which involves commitment D value into every label. In current settings, we use graph that operates with 6 base plus 8 expansion equals 14 total parents for each given node. Each parent is actually a pointer to a different node for a given node. Base parents are used for computing labels for current layer and expansion parents for referencing labels from previous layer. So as you can see here, 0 node doesn't have parents at all. That's why label 0 is computed without referencing other labels. Label 1 can reference only 0 label. Label 2 references label 0 and label 1, and so on. For the first layer, we don't use expansion part of parents, since we don't have previous layers. So 8 last values of parents array produced by graph object are actually ignored. They are marked by dashes. For the second and further layers, we start using expansion part of parents which graph produces. That means that we bind second layer to the first one. Again, since 0 node doesn't have parents, label 0 doesn't reference previous labels, first label can reference a 0 label, and since we already have previously generated layer 1, we can reference labels from it. They are marked pink. Encoding process is continuing up to producing final layer of encodings, which is 11th in current settings. And now there is a question how to incorporate this process into sealing, as this is our ultimate goal. This is performed in the following way. Sectors nodes form a tree which we call 3D. Final encoding layer that we so slowly computed form a tree called 3C. Then every sector's node is summed with correspondent label from final encoding layer modulo 254 according to current settings, and form a tree called 3R-last. Finally, all those trees produce inclusion proofs for provided challenges. These inclusion proofs obtained from 3 distinct trees are combined together into the object that we call vanilla proofs, which is an actual proof that certifies correct registering new sector in the network. Replica ID is also part of vanilla proofs object, which is essential as it is also committed to the blockchain and allows any validator of vanilla proofs to check all bindings between sector, miner, and chain. Since vanilla proofs object can take megabytes for production Filecoin sectors, it is quite problematic to keep this information for each sector in the blockchain, and also maintain transferring this data through the network. That is why we use SNARK primitive that allows compressing vanilla proofs object into succinct argument of knowledge that has much smaller size, 192 bytes for a single Groth16 SNARK proof. Interesting point is that we don't use zero knowledge property of SNARK primitive because values of vanilla proofs are not secret. The only property of SNARK that is relevant for Filecoin is its succinctness property. Of course, usage of SNARK's primitive requires global parameters accessible for both prover and verifier. They are generated via trusted setup ceremony on blockchain Genesis. If you follow the link below, you will see that we have a bunch of parameters for each proof type, including PoRep, and also for each sector size. Publishing succinct SNARK proof instead of large vanilla proof is obviously beneficial, and any other participants in the network can use SNARK verifier with corresponding global parameters to validate correctness of replication. Okay, now after producing short SNARK PoRep proof, storage provider can remove data required for a 3D and 3C construction, actual data of the sector and final encoding layer, and store only sealed sectors data, which is actually an encoded replica and some additional metadata. Talking about actual numbers, the duration of sealing heavily depends on CPU type, whether it's Intel or AMD. Fastest sealing is achieved on AMD CPUs due to its SHA-256 intrinsics. According to our latest results for 32 GIP sector, producing single encoding layer takes approximately 22 minutes, while sealing 11 layers are generated, so in total it takes approximately 4 hours in current settings. So the link below refers to our build bot, which we use for such experiments, and includes data about actual software and hardware. Summarizing all the above, proof of replication is an essential part of sealing process performed while uploading and publishing new sector in Filecoin's network. It cryptographically enforces miners' liability to start storing particular sector in its storage from a given epoch. It satisfies key high-level design requirements of the protocol and protects against fundamental threats to decentralized storage provider by binding actual data to the sector in the storage of particular storage provider, which actually provides security against a cyber attack, since changing identity of already registered sector will lead to changing the prover ID and consequently the replica ID, which is used while SNARK proof computation. Moreover, it provides security against generation attack when miner attempts to generate sectors by demand using small program instead of actually storing them, trying to increase self-likelihood of winning the block reward. Making sealing process computationally expensive prevents this, as miner cannot quickly generate large amount of fake sectors. However, nothing actually prevents miner to outsource the sealed sector to third-party storage provider and fetch it while retrieval request, as PoRep doesn't guarantee that data is stored for some time after replication. This is the task for another proving mechanism, proof of spacetime. As we discussed, PoRep is used by miner for committing available capacity to the network while registering new empty sector. And in order to prevent outsourcing attack mentioned above, a window proof of spacetime is introduced. Here I need to refer to a couple of external services, which is DRAND, distributed randomness, and clocks, based on NTP protocol that Filecoins relies on. DRAND produces randomness with a couple of properties critical for decentralized nature of Filecoin. First of all, DRAND's initial seed, which is essential for every pseudo-random generator, is generated through a multi-party computation between a diverse set of reputable entities on the internet, like Cloudflare, Kudelski Security, Protocol Labs, UCL, and other, which guarantees its transparency. For each randomness producing request to DRAND, a threshold of those entities is required to generate actual output, so there is no central point of failure. And moreover, DRAND mechanism produces publicly verifiable and unbiased randomness, so any third party can fetch it and cryptographically verify its authenticity, making sure it hasn't been tampered. Clocks is also quite essential for Filecoin. Protocol has strong requirements to clock deviation and enforces every entity to run NTP daemon synchronized with reliable external services. It's Cloudflare, Google, NIST, and some other. So, relying on DRAND and clocks, the idea of Filecoin's proof of spacetime is following. According to current consensus rules, every 24 hours time window is divided into 48 30-minute slots. Filecoin network requests every storage provider to submit particular evidence that previously committed sectors are definitely stored in miner's memory. To do so, network randomly selects particular slot, provides set of challenges, and asks miner to respond to these challenges. If miner does not respond in time or respond in valid post proofs for a particular sector committed previously, network treats that this sector is not available anymore and the mining power of this miner is reduced. Having that this process is continuous, miner has only limited capability to somehow delegate storing of committed sectors to third-party provider. Technically, it works as following. Having a set of sealed sectors in its storage, miner creates instance of trier last from each sealed sector, labeled from 1 to n. Network uses drand as a source of randomness and provides set of challenges that miner should address. Each individual trier last for each sector generates Merkle proofs for a given challenges, grouped together into vanilla proofs object that are finally being compressed into succinct SNARK proof. Here it is shown in more formal what is going on. Every sealed sector, which is actually an encoded sector plaintext data, is used to instantiate trier last, and vanilla proofs builder uses this tree to create inclusion proofs for provided set of challenges. As you can see, unlike PoRep, here we don't need to generate encoding from scratch, so proof of spacetime mechanism works much faster. Note that here, unlike PoRep, we deal with multiple sectors. That is why vanilla proofs builder takes set of replica IDs, one for each proven sector. Finally, vanilla proofs are passed to SNARK prover for compression. As the structure of vanilla proof is different for post mechanisms, we have separate set of global parameters for each sector size, started from proof of spacetime fallback string, which also was generated while trusted setup. Similar to PoRep, publishing succinct SNARK proof instead of large vanilla proof, especially if miner has significant power storing a lot of sectors, is obviously beneficial, and any other participant in the network can use SNARK verifier with corresponding global parameters to validate correctness of spacetime proving. Okay, now summarizing window proof of spacetime, one can say that it accompanies proof of replication in high-level protocol design by providing security against outsourcing attacks when miners try to delegate storing sealed sector to third-party storage provider. Its continuous nature makes mentioned delegation unreasonable, as a malicious miner needs to perform transferring sealed sectors back and forth anytime when WindowPoSt proof is requested. In the rest of the talk, I will cover winning proof of spacetime and election proofs, as they serve for protecting against important practical security issues related to blockchains in general and to proof-of-stake blockchains in particular. Let's start from winning proof of spacetime. Essentially, these proofs are very quite similar to WindowPoSt proofs, but single WinningPoSt proof covers only single randomly selected sector for the storage provider. Current consensus rules dictate that new block should appear in the network every 30 seconds, so once new block is being generated, network agrees on the set of challenges and also an index of the sector to use for addressing the challenges for the storage provider elected to mine this new block. If storage provider is not able to produce valid WinningPoSt proof within short 30 seconds time window, it is not allowed to mine a block. There are no specific high-level cryptographic or security requirement for this proof, only practical one. It ensures that given block is mined by a legitimate storage provider, storing active proving sectors, and not some sort of cheat or spoof from malicious entities in the network. Schematically, it can be described as following. Again, similar to WindowPoSt, storage provider keeps n sectors in its storage. Once it is elected to mine a block, network generates index between 1 and n that points to particular sector in miner storage and challenges for this sector. Rest of the logic is the same as in WindowPoSt. In a bit more details, sealed sector specifically selected by the network is used to instantiate trier last, and Vanilla Proofs Builder uses this tree to create inclusion proofs for provided set of challenges. One can see that WinningPoSt works always with only one specific sector, so size of Vanilla Proofs is smaller comparing to PoRep and WindowPoSt Proofs. Finally, Vanilla Proofs are passed to SNARK prover for compression. Here, structure of Vanilla Proof is similar for both Window and WinningPoSt mechanisms, so we use common set of global parameters for each sector size. And as it was mentioned, WinningPoSt proofs are used together with Filecoin Proofs while new block creation, so I'll abstractly describe election proofs and then we'll summarize WinningPoSt and election proofs together. The consensus used in Filecoin is actually a proof of stake, where stake is measured in amount of useful storage provided to the network. The way how miner is selected for block creation is called secret leader election, and the election proof actually demonstrates that a given miner won the secret leader election, so it acquires the right to submit its block to the chain. And this is how it works in a bit more details. Let's consider a toy example with 3 storage providers, where storage provider 1 has 4 storage sectors, A1, A4, storage provider 2 has 2 sectors, B1, B2, and storage provider 3 has 3 sectors, C1, C3. Here on the slide, SK and PK pairs are private and public keys of particular storage provider. The probability to win the secret leader election will be approximately 43% for first storage provider, 33% for third storage provider, and 24% for second, according to the amount of storage they provide to the network. You may notice that Flashing Miner is a storage provider that wins secret leader election for current epoch, and storage provider 1, as it has 43% of power, flashes more frequently. Every epoch, each storage provider in the network which participates in mining blocks takes a set of messages from the pool and generate a candidate for a new block with election proof computed from the derent value based on current epoch, plus storage provider secret key. A VRF function can be treated as a digital signature cryptographic primitive that allows signing particular data with private key and supports signature verification via public key of signer by any interested entity in the network. Once election proof is computed, storage provider sends this block candidate to the network and at the same time receives from the network block candidates created by other storage providers. In that way, all storage providers that participate in secret leader election have set of block candidates which includes own block candidate, and this set is evaluated and block candidate with heaviest weight is selected as a new block of the chain. Below there are links to how Filecoin computes block weight, and essentially heaviest chain should reflect the most amount of work performed, or in Filecoin's case, the biggest amount of committed storage. In order to check which storage provider was the author of heaviest weight block, the election proof is verified, similar to verification of digital signature, and the winner of secret leader election obtains right to include his block into the chain and collect reward for this block. As length of election proof is not large, it's the only proving mechanism that doesn't use SNARK primitive. So that's the idea behind the election proof. Okay, now let's summarize WinningPoSt and election proofs. Main motivation behind them is making creation of new block fair and secure, enforcing secret leader election process, and proof of storage stake consensus rules of Filecoin. Besides that, these proofs have some important role in securing Filecoin against practical attacks like grinding, when malicious miner tries to manipulate with randomness used via election protocol. That's the task for election proof, actually, having that it relies only on randomness from DRAND, which is secure against grinding by its design. Also, as storage provider is required to submit WinningPoSt proof while new block inclusion into the chain, this guarantees that miner is legitimate storage provider that stores active proving sectors with the data useful for the network, and not some sort of cheat or a spoof. Okay, we have discussed quite a lot proving mechanisms that satisfy design and security requirements of Filecoin. However, updating the data of existing sectors wasn't covered yet. As we discussed previously, PoRep is used while sealing the sector when miner commits capacity to the network. Eventually, after making a deals with users, storage provider engages to store users' data, and in order to fill registered sectors with users' data, storage provider performs upgrading sealing sector. Let's return a bit to the results of n sectors replication. Remember that sealed sector is actually plain text data n0 and x encoded with labels label 0, label x, produced as an output of computationally expensive encoding process. And in theory, we cannot change sectors data directly as it is encoded, so most straightforward way of upgrading is resealing the modified data from scratch, removing data from the storage, and finally replacing the sector that is upgraded with newly sealed sector, which is sector n mark. So after upgrading, network start treating this sector as a completely new sector. This approach for upgrading was used initially in Filecoin implementation. There is also a practical use case when sector is empty from users' data. We call such sectors as committed capacity sectors, meaning that they are actually replications of zero data. And currently, such sectors represent the vast majority. It's 90+% of sectors in Filecoin. For this use case, there is a specific protocol that is called snap deals. Its details are available with the links below. Essentially, due to particularities of encoding, using, so to speak, reversible modular addition operation, it allows reusing encoding labels generated while initial expensive sealing and avoiding modifying the sector's data and resealing at cost of additional storage, which is obviously beneficial for current state of Filecoin. Snap deals is implemented as a separate mechanism called sector upgrade. It involves SNARK primitive usage. That's why while talking about upgrading, we treat it as a separate proving mechanism. But it is a bit out of scope of current talk. So that is mostly it regarding proving mechanisms used in Filecoin. I only want to stop a bit on Grot16 Halo 2 SNARK system replacement, which is actually the task number 1 for our team. As you might notice, SNARK primitive is quite important building block that Filecoin uses while compressing vanilla proofs object, as it can reach 2 megabytes, and it becomes a problem supporting transfers of this data within the network and maintaining it in the blockchain. But the cost of this compression is inconvenient centralized trusted setup required for generating global parameters for SNARK prover and verifier, which is the case for current SNARK system, Grot16. Halo 2 is a potential long-term replacement, and it tries to eliminate some limitation inherent to Grot16 We currently are in progress of investigating potential benefits and optimizations that may improve Filecoin scalability. I think my colleagues Volker already touched this work direction, and Shawn will elaborate in more details while presenting our roadmap for the next year. Final thing that I would mention is that we have huge Rust codebase that implements all described proving stack, and we in FilCrypto we really welcome external contributors to participate, and looking forward to collaborate with the rest of the teams in the PL ecosystem. Thanks for your attention, and we'll try to answer your question.
Okay, so we are now ready for the question and answers. So I have Artem also on Slack to answer questions. He has a bit of a delay, like 10 seconds, because he's watching the stream. But yeah, but I can also help to answer questions. So are there any questions? Okay.
So one thing that came up was that the snarks used for PoRep and posts don't have zero-knowledge properties, which was probably made for some trade-off. Do you know like what we got out of not having actual zero knowledge over those proofs?
I can answer that one. So we don't use the property. Currently, the system still uses the zero knowledge part, but there's a PR open to remove it. But it's really only, it makes only it doesn't make much difference in the performance, basically. But basically, we figured out that we actually don't use this property, so we could remove it, but yeah.
So we do actually use it right now on mainnet?
Yeah, so we actually do use it. So the proving system is using it without actually we needing it, yes.
Cool.
Hey, thanks a lot for this. This is incredibly useful. I've been waiting a long time to get a walkthrough like this, and I think a lot of people have. I'm interested in that kind of the heart of this, which was the proof-of-replication process itself, what we call the sealing process, where we started off by breaking your data, or essentially merkling your data into, in this example, we used 15 leaves, and then going layer by layer, essentially constructing these labels, right? And the next layer is based on the previous layer's labels. What do we keep at the very end of it all? So I assume we don't keep all of the layers that we've constructed. What is the final thing that we actually preserve and that we need to keep for posts and so on? So essentially, what's in the replica?
Yeah. I hope to get Artem's help, but I can start answering, but I hope I will get his answer as well. We certainly keep the replica itself, obviously. I will.
I believe all the Merkle trees as well.
Yeah, so we can
Tree R last, all the Merkle information, I believe, gets stored away.
So we keep the last layer, essentially, is what I'm saying? Okay, cool. In that case, what is the unsealing process like? Because I know we can do it, because I know you can unseal the sector, but I don't see how from that last layer you can go back to the unsealed data.
Yeah, so this is quite simple, actually. So the last layer of the sealing process, so the layer 11, basically, that's not the replica. Okay. That's just the replica key, so I would call it a replica key, and that one is used, this one is applied to the original data, and then you get the replica out. And as we already work on like cryptographic primitives, it's in the cryptographic space, it's just an addition, and to unseal again, you do a subtraction, basically. So you can think of, if you are like familiar with an XOR operation, it's the same thing. So use the key, do an XOR on to get the replica, and to get the original data back, you do an XOR again.
So what are the two things being XOR'd at that step?
So the layer 11 is the key, okay, and you do XOR it with the original data and get the replica out.
Gotcha. So you keep the original data around.
Just checking if it's correct what I'm saying.
Yeah, well, Artem was just saying that it's the nodes plus labels that actually get stored after the sealing process.
Cool. In that case, how long does unsealing take? Because I thought it was a computationally intensive process, but if we're just XORing some data, shouldn't that be quick?
Well, it's it is kind of like an XOR, but it's a cryptographic like operation, so it's like not as fast. So.
Regenerate the whole sealing key. So you can seal again to get that, but you then XOR.
Okay, unless you keep it right.
Yeah, except if you keep the key, of course. Right. So then it's fast. Okay.
Cool. Thanks a lot.
Yeah.
Other questions? Otherwise, we can go into the roadmap for the next year. Just over here.
Yeah.
So as an SP, one of the things that we really care about is to plan ahead. And every time there's a performance upgrade to the proofs, it basically means the size of our seeding cluster could change, or like the balancing or the size. Now we also have sealing as a service coming in. I was just wondering if you could share some light on what your roadmap looks like for improvements. Now, one thing is Halo 2, but I see as an SP that does not really worry me much. That's probably more about the trusted setup. But from an actually like sealing performance, are we looking into getting like much faster sealing soon? Because that could impact if we are going to sell excess capacity as sealing as a service. Yeah, stuff like that. So do you have any, like, I don't know if it's a short answer, but any ideas about if something will happen?
Yeah, so we will have the roadmap soon. So the short answer is we are fully concentrating on Halo 2 now. So I won't expect any improvements soon. But so we get into the roadmap is a perfect question for.
Right. So the CryptoNet Labs, which is basically the research end of proofs, they're looking into some things regarding speeding up the sealing process. Yep. So as far as our roadmap for the next year, Artem already talked about this a bit. A little bit of background on it. Halo 2 is a ZK SNARK that's developed by the makers of Zcash, electric coin company. So we're working on incorporating that into Filecoin Proofs with their assistance. Also something that we've touched on, that it eliminates the trusted setup process for Groth16. So this is really important for us in the future now to deliver different types of proofs, such as with FVM or compute over data, beyond just the current proofs with Filecoin proof of spacetime on the network. It'll also accelerate any bug fixes or anything that needs to be rolled out on the network, since we no longer have to do this months-long trusted setup process. One thing that's important to note is Groth16 is not going to be going away, so they're going to be supported side by side. It will be expected, though, that future use cases, especially with compute over data or any proofs off-chain, are going to be Halo 2, at least immediately, but possibly some features will be Halo 2 exclusive. So I kind of touched on both of these. This is kind of our roadmap. So the quarter that we're in currently, we're working on getting functional parity right now between Groth16 and Halo 2, making sure that all our dependent Rust libraries are up to date. Volker is also working heavily on getting GPU acceleration up for Halo 2. So all non-recursive circuit code we plan to have done this quarter. Really what we want to have by the end of 2022 is a library that's available so that any of the Filecoin clients can begin to start incorporating it and start their own development cycles off. Going into Q1, we're looking to have proof recursion fully integrated. So any generating proofs of proofs, also continuing our optimizations, getting feedback from any of our development partners, especially the client development with Lotus and Venus and Forest, and using that to come up with a final API, get it in a draft of the FIP available. We also plan to start external code audits, with Electric Coin Company, as well as any other security audits to make sure our code is robust. In Q2, so planning to have it ready to get it to production state, to have the API refined, and have a FIP, be ready to have a FIP out for vote. And this will also be some of the final testing performance gathering. So we'll have a better idea at that point how the final performance lines up with Groth 16. So Q3 is going to be probably the biggest change for our team. So up until now, we focused entirely on proofs for specific to the Filecoin chain proofs. We'll be looking more at other use cases so that the Filecoin proofs library will be able to be used for more generic proofs, like some potential use cases we're looking at are chain snapshots and chain bootstrapping to allow lightweight client nodes. Also integration with smart contracts to prove arbitrary proofs. Also looking at possibilities with L2, L3 networks, so compute over data, possibly integrated with WASM. Lurk is another project that we're looking at integrations with, so verifiable compute. So it's really up in the air, but it's our main goal for Q3 is sort of unlocking the proofs library to allow more generic proofs. So that's it. This is where to find us. We have a Slack channel, FilProofs, which is an open channel anyone can join. These are a few of our projects. Rust FilProofs is really the meat of it. The project where you can dive into all the code. Rust Filecoin Proofs is our external API condensed into one place. And you can find our crate with all the dependencies on crates.io. So it's a Rust-based project. Filecoin-proofs-API. So any questions anyone has regarding a roadmap? Let's go back there.
Not specifically roadmap, but what keeps you up at night, I guess? Like the proofs, like you talked about scaling or adding another layer to the proof of PoRep if, you know, CPU speeds or GPU speeds go up really high. What are the things that you guys look out for in terms of like making sure it's secure?
Volker has the most tenure here, so maybe you should answer that. For me, I would say getting adequate test coverage, especially for making sure that every hole is plugged, that we have coverage for everything, especially with Halo 2, which is a huge change coming down the pipe. You want to go ahead and give your answer? For what keeps you up at night with?
Good question. What keeps me up? Yeah, I would. I'd really like to make it like using less resources, basically. So coming up with something that is more efficient would be great, but I know the limitations of the cryptography. So yeah, but this would be great if we find better ways to use less resources, but having the same security properties, basically.
Right. So again, as an SP, what we're facing is basically when we talk to clients is that we need to tell them that Filecoin is really cool because we are actually verifying that we have the data. But we also have to tell them that we use quite a lot of energy on making that happen. That's partly of the sealing process. I don't consider the proving afterwards to be such a big thing, but especially the sealing. Meaning that for example, for 40 racks, we might have 10 of them filled up with compute that does nothing else than PoRep. If there is speed-ups available out there, even getting open sourced, Is it because of constraints in your team that you're not like pushing for getting that speed up implemented right away versus Halo 2, for example? Because I feel like also talking to the Filecoin Green team, this is one of our pain points, is that we have this very high consumption of power on doing this part of the process. And I guess as an SP, where we want to go is, in the future, we'll see that this gets smaller and smaller. But part of that would be to make sure that, we are always aiming at getting faster seeding speeds, taking up less resources and so on. But it seems like right now, since we got the last speed updates on the C2 and PC2, I think, it has been a long time since we've seen anything. And we know out there's a lot of SPs that are starting to develop their own stuff. There is a lot of implementations or like speed ups being done out there, but not really implemented centrally. And I guess implementing it centrally would mean that it comes out to more SPs and then generally using less energy. So is that something that you're, is that something that is that because of like lack of resources or what is going on?
So there's two things. So I would say, so there are pieces in the seeding process, especially the first piece of the seeding process is especially expensive. But so the GPU parts basically are just slow. So they are not intentionally slow. They're just slow based because snarks are slow. So we hope that there will be breakthroughs in research where basically this will basically for free kind of in the future. But the first part is really like this is where you get the security into the protocol to make sure you really have the data. And that's intentionally computational intensive because this is how you can make sure it's secure. There are certain improvements, but it's not like, there could be improvements on RAM usage, for example, but really like the CPU usage, for example, I currently don't see a way to get away with it except doing like a completely new PoRep. In regards to the optimizations, yeah, I would say it's a lack of people working on it, but also like people are free to contribute. So I can see that the problem is there's the problem of course, it's beneficial for miners to hold this information back because they have an advantage. But if people would contribute, we would surely like look into it and yeah. Cool, all right. I think we have to close the Q&A, so thanks for the questions. And yeah.